Welcome back to Calculus 2. Section 5.3, the Divergence and Integral Tests. Sections 5.1 and 5.2 introduced sequences and series. The big question is the convergence of sequences and series. 5.3 begins our journey on convergence tests. In this section, we'll introduce two tests of convergence, the divergence test and the integral test. Let's get started. Now, if we want to talk about convergence of a series, let's go back and think what the definition is. A series converges to a finite number s if and only if the limit of the partial sums s sub k is that finite value s. Here on the left-hand side of the if and only if symbol, we have a series. It's an infinite series. And we have a finite value s, and we're putting an equal sign between them to represent the notion that this series is a representation of finite value s. So the left-hand side is saying that we have a convergent series. By definition, what does it mean for a series to converge? If instead of taking 1 to infinity, all terms of the sequence, we only take 1 to k, that's the kth partial sum, denoted s sub k. That value will exist for every integer k. Thus, we'll have a sequence of terms. So s sub k is a term in a sequence. And then we can look at the limit of that sequence. And if the limit of that sequence is s, then by definition, the series converges. Very nice. Now, when we're looking at a series, there is a sequence associated with the series. The terms of the sequence are given by a sub n. Let's use the notation a sub k. So if we want to look at the kth term in the sequence of a's, we could add up all of the terms up to k and then subtract away all of the terms coming before the kth term. Then this difference is exactly the kth term. All right, well, how is that useful? Well, if we assume that we're going to have a convergent series, then the sequence of partial sums is going to converge. And writing out the kth partial sum versus the k minus first partial sum, each is going to limit to the same value. So if we take this equation and we put a limit on either side, and then make the assumption that the sequence of partial sums actually converges to a finite value, then we have the nice condition that on the right-hand side, we're going to come up with the difference of s and s, which is 0. Okay, so let's look at this logic, but in reverse. So if we have that the terms of the sequence a sub k do not tend to 0, then it cannot be that the sequence of partial sums converges to s. Right? Now, this is then exactly the divergence test. And notice how we flipped things around, that we started with an assumption that if the terms of the sequence do not tend to 0, then convergence is out the window. Okay, let's make that statement, the divergence test, that we have to have the terms of the sequence tending to 0 in order to have convergence of the series. Flipping that around, if we do not have terms tending to 0, then the series must diverge. So terms tending to 0 is a necessary condition for convergence, but it is not sufficient. Right, so it's necessary but not sufficient. Okay, divergence test. Let's do an example of applying it. All right. So let's have a series. And whenever you look at a series, you want to look at the associated sequence. The associated sequence has nth term given by the quotient n over n plus 1. If you take extremely large n's, 1,000 and 1,001, there's not much difference between the numerator and denominator. The quotient then is something like 1. Well, that means that for this series, it has an associated sequence where the nth term tends towards 1. That's an easy enough observation. Even more elementary is that 1 is not 0. Thus, by the divergence test, since the terms of the associated sequence do not tend to 0, what does that say for the series? It says that the series must diverge. Now, you'll want to, as we proceed forward with many, many different tests, you'll want to quote what test you used in arriving at your conclusion. So here we've used the divergence test, so DT for divergence test. Nice. All right, so here are some examples for you to play with in applying the divergence test. And the divergence test provides a result of only one kind, that the series diverges. The divergence test does not have a second prong. The divergence test does not provide for convergence. Okay, so if you have that the series diverges, you state that. If the terms of the sequence do tend towards 0, the divergence test is inconclusive. Right? So if a(n)'s do tend to 0 as n goes to infinity, then no information is obtained. Okay, so the divergence test can determine whether the series is divergent. The integral test, on the other hand, is double-pronged. It can be used to show convergence as well as divergence. Let's start with divergence. Now, if we're going to employ integrals, we can go back and we can think of the definition of an integral. The definition was the limit of a Riemann sum. Hence, we have drawn in a curve. Area underneath the curve is shaded, as well as approximating rectangles. These rectangles happen to protrude past the curve, and that's because we're using left endpoints in order to evaluate and determine the heights of the boxes. All right. So again, focus on the fact that we have a curve. Let's suppose that the curve, for an example, is 1 over x. And then let's take the bounds of integration to be from 1 up to 8. So draw in the reciprocal function, mark off 1, mark off 8, and then shade underneath the curve. That area is then represented by a definite integral. And make note that we're using f as 1 over x. As a separate picture, let's draw in the rectangles again. And then we could note the rectangles as associated with a sequence where the sequence has general term a sub n given by f at that integer n. So this is going to require that each box has a fixed width of 1, so that when we evaluate at left endpoints, here x is equal to 1, 1 over 1 is 1, the height is 1, the base is 1, therefore the area in this rectangle would be 1. The x's and y's are not to the same scale. Don't worry about that. And then if we look at the next n value, 2, then f at 2 would be 1/2. So the second box has a height of 1/2 and a base of 1. Therefore, the area is given by 1/2, or denoted a sub 2. Very good. The next thing to note is that, as we said earlier, that the rectangles protrude past the curve. Therefore, the area in the rectangle will be greater than the area underneath the curve over the same interval. Very nice. So, the area in the shaded rectangles can be represented through this summation, which is s sub 7. And the area in gray is given by the definite integral. Since the rectangles protrude past the curve, we have the inequality pointing in this direction. All right. Well, this is done for a particular value of k equaling 7. And note that on the integral, in order to correspond with 7 rectangles, we took our bounds from 1 out to 7 plus 1. So if we want to generalize this inequality we established for any value k, then the bounds of integration would be from 1 up to k plus 1. Good. Well, the nice thing is that we have on the right-hand side s sub k. On the left-hand side, we can evaluate the antiderivative of 1 over x is ln of x, evaluated at bounds, produces a difference of logs. Log of 1 is 0. And then log of input, getting larger and larger and larger, will produce larger and larger values. As these larger and larger values are always less than or equal to s sub k, then the limit of s sub k is unbounded, is infinity. Infinity is not a real number. What does that mean? Well, by the definition of convergence of a series, this series diverges. You recognize the series as the harmonic series. In a previous video, we looked at the harmonic series being always bigger than or equal to 1 plus n copies of 1/2. Here, we're using the integral test as a second method to show that the harmonic series diverges. Very good. So we've looked at the divergence test and the integral test as ways in which to show a series diverges. The divergence test is only good for showing divergence. The integral test, on the other hand, is a two-pronged test. It can be used to show convergence as well. Let's do that. So here in this example, let's use our curve as the graph of 1 over x squared. Draw in some rectangles. Note that these rectangles reside below the curve as opposed to the previous example. And that's because in the previous example, we wanted to obtain divergence of the series. And here we're going to obtain convergence of the series. In other words, the area under the curve of the graph will be a larger value, a bounding value, for the area of the partial sums. Okay. And in terms of where we are evaluating, before we evaluated at left endpoints, now we're evaluating at right endpoints in order to produce the heights of the boxes. And then because we're evaluating at right endpoints, our boxes don't begin by being associated with the very first term, but our boxes begin associated with the second term onwards. All right, but that's not a major distinction since we're always able to add in a finite value representing a sub 1. In terms of the picture that we have here, the blue rectangles are represented in the left expression. Summation from n equaling 2 up to 8 of the terms of the sequence given by 1 over n squared. And then the gray shaded region is given by the definite integral. Note that the upper summation bound and the upper integration bound are matching. Thus, if we want to switch over to a similar statement for the first k terms summed, that the upper bound on the integral will be k rather than k plus 1 as we had before. Nice. Now, if we want to introduce the notation s sub k, then we have to add in the first term. Well, the first term would be f at 1. That would be 1 over 1 squared. So s sub k includes 1 in addition to the terms 2 through k. So if we add in a 1 and we subtract a 1, then we have an equivalent expression for the left-hand side. On the right-hand side, however, we have an integrand of x to the negative 2 increments to negative 1, so that when we evaluate it at bounds, 1 and k, we get 1 minus 1 over k. We're interested in s sub k, so let's isolate s sub k by moving the 1 to the other side. 1 plus 1 is 2. 1 over k is a positive quantity. Taken away from 2 means that s sub k will always be controlled by 2. Nice. Now, take a note that 1 over x squared evaluated at n gives us 1 over n squared. Those are the terms for the associated sequence. That these terms are always positive valued. That the positive valued terms are decreasing in size. But that by having positive values added in to the partial sum means that the partial sums will increase. So simply by taking the terms of the sequence as positive valued, the associated partial sums will be a monotone sequence. They'll be monotone increasing. And what we've just done here is we've shown that the partial sums are, in addition, bounded. And those are the two prongs needed to apply the monotone convergence test. So let's do that. To show that the sequence of partial sums converges by the monotone convergence theorem, we need two things. We need that it's monotone and we need that it's bounded. Well, we're taking a sequence which can be given by a function evaluated at integer values. We get that the sequence is of positive terms. Thus, when we have the kth partial sum to get the next partial sum, we're adding in a positive value, which means that the sequence is monotone increasing. So monotone increasing thanks to the fact that the terms are positive valued. Then the other part of monotone convergence theorem is that the sequence is bounded. Again, because the terms are positive valued, the partial sums will be bounded below by 0. And thanks to the integral, the partial sums are bounded above by 2. So what does the monotone convergence theorem say? It says that the sequence will converge. Okay, so more generally, let's write down the integral test. We've looked at examples, 2 examples. Let's write it down in its generality. What do we need? We want to have a series. We want the series to have positive terms. Remember, this is going to lead to the sequence of partial sums being monotone increasing. Next, for those positive terms, we want them to be given by some function evaluated at integers, and that function, we want it to be continuous, and we want it to decrease. Now, the decreasing part on the function is simply going to mean that it will pass, the series will pass the divergence test. By being decreasing, we want it to tend towards 0, so that the terms of the sequence will tend towards 0. All right? So, unlike the divergence test, the integral test can show both convergence and divergence. So we need to consider 2 different cases. One case where the integral controls from above, and another case where the integral provides a lower bound that blows up. All right. Now, if we were looking to control from above, like the example that we just finished, remember that we started at the second term and added out to the kth term. As we had to skip over the first term, that's why the first term is appearing here on the right-hand side. Whereas and that's using right endpoints, if we use left endpoints, then we can begin at the first term, but to go out to the kth term, on our bounds of integration, we have to add in 1 to that index k. All right. Let's restate these. So here we're looking at an upper bound on the kth summation. Restate that as the kth partial sum bounded by the first term plus a definite integral. So this will always be true. Then if we have that this integral actually converges to a value, so that's the statement here, if it actually converges to a value, then the kth partial sums are bounded above. But since we're using positive termed sequences, the sequence of partial sums is going to be monotone, increasing. As well, it's going to be bounded below by 0. Thus, we can apply the monotone convergence theorem to say that the sequence of partial sums converges. And by definition, we get that the series converges. All right, so the integral test can be used to show convergence of the series, unlike the divergence test. But the integral test can also be used to show that a series diverges, like we did in our example, showing that in a second way that the harmonic series diverges. So how is that done? Well, the kth partial sum is going to always be bigger than, under the given conditions, the definite integral from 1 out to the index plus 1. So if we find that this quantity blows up if it diverges to infinity, then the sequence of partial sums is going to be unbounded, which means that it cannot, the sequence of partial sums, converge. And if the sequence of partial sums does not converge, then the series does not converge, i.e., it diverges. All right. Now, a nice thing is that the integral test, which requires positive terms given by some function, which is continuous and decreasing, says that the behavior of the integral and the series go hand in hand. If the integral converges, so does the series. On the other hand, if the integral diverges, then so does the series. All right, so more formally, in a more compact way, we can write down the integral test as a series with positive terms an and a function f, which is continuous and decreasing, such that for some n, the terms of the sequence are given by the function at that index after some starting point capital N. Then the behavior of the series and the integral will either both converge or both diverge. Nice. So that's the integral test. Here are some examples for you to play with. Excellent. And remember, the integral test may be used to show either convergence or divergence. Good. Whereas the divergence test, recall, can only be used to show divergence. Now that we have the integral test, if you think back to the previous video where we introduced the harmonic series, which we know diverges, and the geometric series. The geometric series has a simple test of convergence. Think back, do you recall the condition for the convergence of a geometric series? Something that you want to have always at the front of your mind when going through chapter 5. Pause the video if you don't recall. The harmonic series is actually a p-series. So let's discover why that is the case. Let's make the definition of a p-series. So for any real number p, the series summation from n equaling 1 out to infinity of 1 over the index raised to this p, fixed value p, is called a p-series. All right, quick quiz. What is the value of p which gives the harmonic series? Well, the harmonic series is 1 over n, and that would require that p equals 1. Second question, is the harmonic series convergent or divergent? Pause the video if you're not sure and go back and check. All right, we've actually, in looking at the integral test, also considered a p-series for p equaling 2. Same thing, pause the video if you're not sure whether p equaling 2 led to a convergent or divergent series. All right, so we've actually seen p equaling 1, p equaling 2, two instances of a p-series, and here all that we're doing is generalizing that. And what we want to do is we want to think about what are all of the p's that lead to convergent p-series? What are all the p-values that lead to divergent p-series? So the harmonic diverges. In the case of p equaling 2, we saw in our previous example, converges thanks to the integral test. Now, in this video, we've also done the divergence test. So let's consider for any p-value, which is negative. That means that this n is going to pop up into the numerator, and we're letting n go out to infinity. Therefore, the terms a sub n in a p-series with p being negative do not tend towards 0. Likewise, if p is equal to 0, we're taking the limit of 1, and 1 is, again, not 0. So, for p less than or equal to 0, the p-series diverges. Wow. we're off to a pretty good start here. Let's record this down. That we know for non-positive p's, the p-series diverges. For the positive p equaling 1, i.e. the harmonic, we have a divergent p-series. And thanks to our integral test example, p equaling 2, we have a convergent p-series. Let's consider the convergence for all other p-values. For simplicity, we'll take p to be positive, but not equal to 1, so that the form of this definite integral can be evaluated as integrand x to the negative p would increment up to 1 minus p. If we want to place that in the denominator, we can swap that around and call that k raised to the p minus 1 when we evaluate at bounds. Now, in performing the integral test, we'll want to take the limit as k goes to infinity. Remember that p is just a constant. 1 is a constant. We're looking at this difference. We would like this difference to be a finite value. In the limit as k goes out to infinity, well, that's going to require the k getting really, really large, staying in the denominator so that this term goes to 0. K popping up to the numerator, and that term will go out to infinity. And limiting to infinity is not a finite value. Therefore, we want the power on k to be positive. Another way to state that is that we require that p be strictly greater than 1. Nice. So when we come in and we apply a limit on either side, taking the limit on the left-hand side, on the right-hand side, this term will tend to 0. We can bring this negative 1, push it through, and we'll get that 1 over p minus 1, when we push the negative, is a finite value. Thus, our p-series will converge whenever p is strictly greater than 1, thanks to the integral test. Indeed, we already considered the p equaling 2 case and found convergence. Here, by our calculation and the integral test, we're finding that for any p strictly bigger than 1, the associated p-series converges. Very good. So we can update our findings that p strictly greater than 1 leads to a convergent p-series. And then looking at the case of p trapped between 0 and 1, repeating our computation, but for now, 1 minus p is going to be a positive value. In other words, p minus 1 is a negative value, so k pops to the numerator. Letting k go out to infinity, we get infinity in the limit. And thus, by the integral test, we find that the integral diverges, and therefore the series also diverges. And then for a p-series, the test is rather simple. P's must be strictly greater than 1 in order for the p-series to converge, and p's must be less than or equal to 1 for the p-series to diverge. Recall on the geometric series, it was the absolute value of the common ratio be strictly less than 1. All right, so now we can add to the geometric series the p-series. Good. So here are some p-series for you to play with, and just use the test, identify the p, and is it strictly bigger than 1 or less than or equal to 1? Good. Now, in a setting like engineering, you might want to do a computation, and therefore you'll need a value. In calculus, calculus is a lot about taking a limit. And in that limiting process, well, when do we have a good value comes down to how much error is present. To study convergence of a series, we looked at the limit of partial sums. So now, looking at that partial sum, if we add in, which is the sum of the first n terms, if we add in the rest of the terms, then we'll have the entire series. So we'll now call the rest of the terms capital R for remainder. So in our picture here, we're looking at the first 7 terms added up for S sub 7. And then the remainder is going to correspond with the sum of the first 7 terms, all remaining terms. So this should be R sub 7. All right. Good. So again, R sub 7 is going to begin at the 8th term and add all remaining terms. Now, the way that we have picked our rectangles, they're protruding past the curve. In other words, we're using left endpoints to find heights of the rectangles, and thus we're getting a value for the remainder to be greater than the associated definite integral from 8 out to infinity. Okay, so what we're doing right now is we're considering, well, if we have a nth partial sum, how accurate is that partial sum? Think of taking just the very first term. You can get an approximation of the entire series value, but only the first term is not going to be a very good estimate. Good in quotations. What do we mean by good? We mean that the remainder is going to be small. So right now we're investigating how we can find some estimates on the remainder. And what we're coming up with here is we're coming up with lower bounds. So again, starting at the 8th term means that our remainder is termed R sub 7. If you've added the first 7, then the remainder would begin at the 8th. And more generally, we can say that the nth remainder will be controlled from below by that index plus 1 out to infinity as bounds on an associated function. Nice. So this is a lower limit. If we turn things around, instead of taking left endpoint, but now use right endpoints to produce the heights of the rectangles, the rectangles would sit below the curve, meaning that this remainder will be of size smaller than associated integral. And note where we're going to have to begin the integral if we want to consider R sub 7, that the associated definite integral would begin at that same index value. Let's write this down. So R sub 7 will be controlled from above, the definite integral beginning at that same index, going out to infinity. And then more generally, for an arbitrary n, R sub n is controlled from above by n out to infinity for bounds on the definite integral of the associated f. Very good. We've come up with a lower bound as well as an upper bound by considering the rectangles having heights found at left endpoints or heights found at right endpoints. Combining these two together, we can then write down a remainder estimate, and we can formalize that into a statement called the remainder estimate. And our assumptions have been that we're taking a series with an associated sequence of positive terms, that those positive terms can be given by a function evaluated at integers after some starting point, where the function is continuous and decreasing. And then under that condition, we can say that the remainder, the nth remainder, is controlled below by the integral, the definite integral of the function from n plus 1 to infinity, that's below, and then above by from n out to infinity. Nice. So in practice, we're going to use this upper bound in terms of providing us with information on the size of the remainder. Okay, so let's do an example. So we'll take a p series with the p equaling 1.3. Recall 1.3 is strictly bigger than 1. Thus, this p series will converge. All right. So let's see what the value of this p series is. Maybe let's get a peek into its value by considering the sum of the first 10 terms. So since this is a p series with p equaling 1, that's 1 over the index raised to the p, plus the next term, 1 over the index raised to the p. If we want s sub 10, that's the sum of the first 10 terms. So we go out to index equaling 10, 1 over 10 raised to the p. We'll need a calculator to come up with the sum, but here's the exact representation of the value. Thanks to a calculator, we come up with a decimal approximation. Okay, so how about the remaining terms? What do they sum up to? Well, that's difficult to say, but we can come up with an estimate for the value of the sum of the remaining terms. And it's rather simply done. It's done through an integral. So remember what the remainder is. It is the sum of all of the terms, but then take away the sum of the first 10 terms. Note that we're putting this in absolute value. P series is going to be a sum of positive terms, so the remainder is going to be positive. Good. And then where do we begin our integral from? We begin it from the index of the remainder. Very nice. This is a straightforward integral to evaluate. When we plug it in, we can come up with a decimal approximation and see that the remainder is controlled by 1.7 approximately. Okay, so then looking at the second part of this question, well, if I only take the first 10 terms, I come up with a value. How good is that value? Well, that value is off by approximately 1.7, or no more than 1.7. Be a nicer way to phrase it. So how many terms do I need to add up? Another s sub n. What s sub n is going to tell me that the quantity that I produce will be within 1/10. Okay, so this is actually something we can easily determine. We repeat our computation. Instead of s sub 10, we're now going to use s sub n, capital N, to come up with an estimate for capital R sub n, which means we want to look at the definite integral from n out to infinity. And plugging that in, note that when you work this out for yourself, I'm skipping the work of evaluating an indefinite integral. You want to make sure to write this out as a limit. Then we come up with the value. Now, this is the controlling value on the remainder. And what we want is that this controlling value itself is less than the given tolerance. We have a tolerance of 1/10. So we want 1/10 to control this controlling estimate. Nice. So this sets up an inequality for which we can isolate the unknown capital N. A bit of algebra brings n to the other side as bigger than this quantity. Plugging that in, we come up with a value. We come up with the left-hand side is approximately 119,196 point something. All right, so the question was, for what n do we get a good estimate? A couple of different ways that we can phrase this. We can say that any n bigger than 119,196 is fine. If we wanted to just specify, well, I want the minimum n value, then that would be 119,197. Right? Since 196 isn't going to do it because of the 0.22, we'd have to round to the next highest integer value. Beautiful. Your turn. For how many terms do you need to add together in order to approximate the true value of this series to within 1/1000th? Nice. And then another one. Here we have a sum of terms where the sum begins at 1 over n and ends at 1 over 2n. And you want to do calculus on this definite integral and then relate that back to the sum, and then try and consider how the sum gets better and better the larger and larger the value n becomes. Nice. So that's the remainder estimate, a common notion that we're going to see again, that we've seen in the past and we'll see again. It finishes up this video. Thank you so much for watching. Please like if you find the video useful. And I will see you on the next one.